Hey there, my name is Alejandro, and welcome back for day 99 of me doing the Daily LeetCode Challenge until I reach 1 year's worth of green contributions here on GitHub. So today's problem is for October 23rd, 2024, and let's get straight into it. Okay, today we get a LeetCode medium, problem 2641, cousins in binary tree 2. Given the root of a binary tree, replace the value of each node in the tree with the sum of all its cousins' values. Okay. Two nodes of a binary tree are cousins if they have the same depth with different parents. Okay, return the root of the modified tree. Okay, note that the depth of a node is the number of edges in the path from the node, from the root node to, oh yeah, okay, so it is actual depth, not just height, okay, yeah, okay, sure. Okay, so let's look at an example. So, whoa, 5, okay, so replace the value of each node in the tree with the sum of all its cousins' value. Two nodes of a binary tree are cousins if they have the same depth with different parents. Okay, so the root node is the only one with a depth of 1. So essentially that will always be 0. Okay. Then, but, so all its cousins but not itself. Interesting. Okay. So, yeah, so the root node is the only one at level 1. It has no parent, but no other node is like that, so that becomes 0. Then from the root node, these are both at level 1 or level 2, but they don't have different parents. So besides themselves, there are no other nodes at that level, at the same level, that have different parents. Interesting. And then from here, okay, so this node is at level 3, and this is the parent. And here's another level 3 node with this parent. So this is level 3 node, but it has this parent. So we should only consider the 7, I see. And then for this one, then yeah, at level 3, there are these two nodes, which both have a different parent, so you take their sum and do that. Okay. That makes sense. Oh, and by the way, sorry, if I'm talking a little lower and everything and so on, or coughing a lot, it is because I am sick. I went hiking this past weekend with one of my friends, and at the very, very top, it was extremely windy. I'm around 200 pounds, and the wind was so strong that it was moving me. It was also very, very cold, and I was wearing the very same hoodie that I'm wearing now, which was not enough to keep me warm up there. And yeah, I ended up, I think, just catching a cold. Hopefully it's just a cold, but yeah, I am a little bit sick at the moment, so please forgive me for that. But otherwise, the very first thing that comes to mind is like, okay, I don't, well, the very first actual thing that comes to mind is just why not focus on step 1, which is just, for each node, just get all pairs of level and parent, right? And essentially, like, these are the values they map to. But everything, okay. Essentially, for each node, I want to find all the pairs of levels that are the same and different parents. Okay, I might find, what are the constraints on this problem? So like 10 to the 4, yeah. It's not necessarily, is it n squared where all the levels are unique? Let's think about it, where is it a balanced tree? Is it necessarily balanced? Like here it's height balanced because like by balance it's like at most difference of 1. Here it also seems balanced. There doesn't seem to be a because if it's height balanced, that's very convenient, but it doesn't seem like they say it anywhere, so I wonder if it is, right? Because, okay, I have to maybe be a little bit trickier. Maybe what I do is something like yesterday, where I get everything at their levels, and not just levels and parents pair, right? Because what's scaring me is if I keep track of a hash map of all unique level and parent node pairs, then it's like if I want to add a node to its correct position, I only want to consider the items that have the same level and different parent, which would require me in the worst case to iterate over all of that, right? So it's like the very first one I only do one iteration, then the second one I do 2, third one I do, well, first 0, second 1, third 2, fourth 3. So it ends up being like 1 plus 2 plus 3 plus da 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 all the way up to n, which if you don't know, something like this, like 1 plus 2 plus 3 plus da 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 plus n, this is equal to n times n plus 1 over 2, which is a factor of n squared, which for this problem will not work, right? The number of nodes is up to 10 to the 5. You can usually get away with up to 10 to the 6, sometimes 10 to the 7 computations of LeetCode. And so here, 10 to the 5 squared is 10 to the 10. There's no way in Narnia you're able to solve the problem. Unless, you know, the height of the tree is logarithmic of this, which it will be in the average case, but they could just have a case where, you know, there's 10 to the 5 nodes and it's just always to the right? Like 1, 2, 3, 4, like essentially, yeah. So I can't assume, they don't tell us that it is balanced anywhere, right? So I can't assume that. Like it's given the root of a binary tree. It's not even a binary search tree, nor is it like, you know, necessarily balanced, it seems. Although from the examples, it looks like it would be. So yeah, this is interesting. So what if, maybe it's more advantageous if I go through all the levels, similar to how I did in yesterday's problem, and then what? Maybe for each level, I keep track of another sub-dictionary, each of which has, you know, a specific parent. Huh? I guess I could do that, right? Or it's like, you know, if I have levels and each of them points to a hash map with their parents, and then whenever I add the nodes, I go to its level. Okay, maybe you know, I map all nodes to their level. Or, okay, I gotta think about this. If I map all nodes to their levels, then that's good information. But then, yeah, I rather either I do, you know, levels to nodes or nodes to levels, but I don't know the nodes that I actually have. Yeah, I'd rather have level to nodes. So levels could point to a list of nodes. It's either, you know, levels is a hash map of like, you know, level to list of node 1, node 2, dot dot dot. For levels is, you know, like a level and it points to a hash map where like parent is like, you know, some parent 1, parent 2, etc. And like maybe these are sums, right? So it's like let's think about it. If I have everything as their levels, so you know what? Let's do that as part 1, right? Let's just def init self dot levels is equal to this, right? Here we'll say self dot populate levels with the root and an additional depth of what, like 0 or 1. Yesterday's problem, it was 1. Here they don't seem to care too much, so we'll say a depth of 0. Yeah. Depth of the node is the number of edges in the path from the root nodes to it. So from the root to the root, that is 0. Okay, so that's essentially how they define it. Now here we'll do populate levels. We'll do from the roots, and there's a depth, right? If not roots, return. Otherwise, self.levels of depth is equal, actually here, if depth not in self.levels, self.levels depth is equal to an empty list. And here we'll do self.levels of depth dot append, you know, the root itself. Why not? Okay, and for now let's just do root dot out. Yeah. That's essentially your daddy. Okay. Then here we'll say self.populate levels with root.left, and self.populate levels with root.right, and here we'll say return. And here why don't we print self.levels and here what do we return? So an empty array at the end. Oh, it's like the okay, so we need to return a tree. Self. Yep. This will be depth plus 1, depth plus 1. And here we'll replace populate levels, because that was yesterday, populate depths. And self.levels, self.depths. There we go, that'll make more sense for the context of this problem. So yeah, 0 has 5, level 1 has 4 and 9, 2 has 1, 10 and 7. So essentially what would be nice is for each node essentially figuring out its cousins, right? Two nodes of a binary tree are cousins if they're the same depth with different parents. Maybe there's like a recursive beauty to this, right? Where it's like, okay, it's like from here, you can only have, between here and here, it's like you can only have, cousins from this pool going with cousins from this pool, right? But then if it's from here, you can have cousins come in from this pool with this pool, and from like this pool and this pool. So that doesn't necessarily work. Sorry. I'm trying to think. Okay, replace the value of each node with some of its cousins' values. Just I'm stuck on how to make this efficient, right? Where it's like, even if I have like a dictionary of like, for each level I still have the parents, right? And then it's like for each one it maps with each other one. But then it's like it's still very, very annoyingly inefficient. Because right, it's like I'm doing n squared work. It's just very not cool, It sucks that you don't include yourself. I'm trying to think. There are hints for this problem in case we need them, and there's a lot of them. 3, okay, 3. Okay. Alright, same depth with different parents. How do we do this efficiently? It's like, yeah, one way was level and parent unique pairs. You might as well have it as level, and then even if you have sub dictionaries as parents, right, where it's just you have because what are these called? Tree nodes, this is just a class, and in Python these are hashable objects, so you can use them as a hashable item for a hash map. So that's not the problem. The problem is, for something like this, right, where it's like, okay, maybe it's like I do something like this is what it used to be, and we do if depth not in self.depths, and self.depths of depth is equal to a dictionary, right? Parent hash comma parent. Parent parent not in self.depths of depth, depths of depth of parent is equal to maybe it's like I do I do an empty list or do I do a value? This is interesting, right? Maybe for now I just do an empty list. Here we'll do root and root, right? Like this is easy to pass in the parent each time. But still, okay, if that's, yeah, so we'll have that. Then we want a dictionary of the parents. And then what do they map to? A value? So we want the cousins. Maybe I do this, right? And then I do for parent in self.depths of depth for instead of parent, okay, I'll call this Papa. Papa, daddy, parent, doesn't matter. Mama, it's all good. Yeah, so for Papa, this is what I don't like, right? This is n squared. It's like every Papa except this one, you know, it gets the whoopsh. Maybe it's like I subtract from the current one, and then at the end it's like I do a parse. Just, I don't like this. Like this is technically, I mean, we can always try, you know, and then it's like, oh, if we time limit exceed, then we time limit exceed. But it's just like technically, like this is where we get into n squared territory. For Papa and self.depth, if Papa doesn't equal parent, self.depth of Papa plus or equal to root.val. And here we might as well add this after the fact in case it wasn't already in there. It's O of 1, but yeah, it's fine. Sum to add root.val to all its cousins sums. Okay, let's print it. Jeez. Wait. What does this even point to? Values. This points to 0. Wait, but I have it by, no, I have it by level. And by level and parent. Oh gosh, this is getting a little wild. Let's print these values. Print I on a loo line each time. Because then it's like we gotta map the nodes themselves to this stuff. For key comma val items, we'll do printf string key equals val equals, why not? Jeez. One, two, three, two, three, two, one, two, three, two, one, 0. So 1, 0. That's the end of the first one. Doesn't give me much info. Depth and self.depths, or papa and self.depths of depth. Print string of the depth of papa equals I don't like this. 0070. Okay, this problem is not that trivial, unironically. Ideally, it's like, we map a node to its cousins. So maybe we don't do the sum stuff yet, and we only do the weird part is that things can only be cousins on the same level. So it's like you separate them by groups, which, yeah, you separate them by parent. So maybe okay, maybe we do both, right? Maybe we map all levels to stuff as well as all nodes to their depth, right? Because if you can know a node's depth, then you go to that depth and your depth's dict, and then you go through all your cousins, right? Anyone that doesn't have the same papa. But then that's still n squared. Frick. How do you do this and not n squared, right? How do you do this not n squared? That is the tricky question. Because, we can't do that, right? So node to depth of root is equal to depth. There we go. Just how do you do this in not n squared time? That's what's crazy. Okay, it's at least a better optimization than just slapping every node at that level in there and then looping through all those ones. At least you'll skip anyone that's the same parent, but it's like the same parent is so little. You know what I'm saying? Maybe it's like, you know, you add it to everything, and then at the end you do like some O(n) parse, so like subtract the needed values from everything you need to subtract it from, right? Some crazy idea like that. Okay. Parent 9 there, then yeah. We can always try, you know, the n squared way. So for papa, instead of the depths, if papa doesn't equal parent, then dot papa dot append my beautiful child. But yeah, the point is I'm adding this root so many times to everything that's not its papa. So inefficient. Or maybe no. Maybe I do it this way. I do keep track of the sums instead. Also, maybe I have to do the other way. This might matter as well. Right, just because it's like, yeah. First of all, let's print these results. Yeah, I guess it doesn't matter. Whatever, we might as well do a post order instead of pre-order. Yeah, okay, I just gotta think about this a little bit. The right way to do this. It's like, let's say you knew for each node all of its cousins. Then yeah, you take those sums. But it's like, are there not like n squared, like, you know, your cousin relationships? But it's like, ideally for a node, you do what? Like find all of its cousins and then each other, you know, you add the numbers. It's like, isn't there like, you know, up to n squared amount of cousins up in there? Okay. Oh my god. Okay. We gotta think. Yeah, okay. Two nodes are, yeah, are there cousins if there's same depth and different parents? That's just wild. Like, as the tree gets big, most nodes will not have the same parent. It will be very rare for nodes to have the same parent. So the number of cousins you'll have is huge. It'll be in proportion to essentially all the nodes inside of your level except for one of them. It's like, if anything, you might as well add the sum to everything. And then for each one, it's like maybe we should flip this problem, right? It's like, take the sum of everything, and then it's like wherever there's, not a cousin, there's like subtract something. It's just I'm having a hard time wrapping my head around that immediately. But there's probably some idea there, right? Otherwise, okay, we try to do this, the good way. Also, depth equals papa dot val equals depth of 0. There's a papa of nothing. Depth of 1. There's only this papa. So yeah, these two nodes will have nothing. And at depth of level 2, there's 7. Whoa, 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 whoa. Yeah, it's 0. This is what I mean. I don't get to the other guys in time. Does that get fixed with in order? No, it does not. So yeah, maybe I will probably require 2 parsings. Where it's like, yeah, I want to do things. I want to traverse the tree in level order as I do this, right? I can't essentially do DFS. So, okay, we'll do def populate depths. We'll do a BFS. So here we'll do root, depth, and parent. Here we'll have a, okay, so we need to do a BFS. So we'll say Q is equal to collections.deck with just a, well, we'll have what? Like root, depth, and parent inside of it. Yeah. While Q is greater than 0. Root, comma, depth, comma, parent. I don't care that I'm overriding these guys. If anything, I'll call these like this. And there we go. Nice. Q dot pop left. If root dot left. Q dot append to root dot left, a depth +1, and the root. And similarly for if root dot right. Q dot append, root dot right, depth +1, and root. And what was the work that we wanted to do otherwise, right? This stuff. So we'll do something like this. Yeah, depth not in depths, then there we go. If parent not in there, s equal to 0, then it sums, and there we go. So here, why don't we do something like this with populate depths BFS. Now what does this give us? It's actually the same. Oh, because it's still, again, it's the left to right problem. Gosh, okay. I don't think. I also have some nuts that are still with me that I brought to the hike. So you know what? These might be a good source of energy as I solve this problem. I don't know if this is good food for when you're sick, but it sure helps. Okay. So yeah, the problem is when we get to these guys, we've never visited this dude before. Can we do something about this? Maybe something like this. Damn. Okay, let's see now. Okay. So now we're over 7 and 11. Because we add things, so it's like between the 4 and the 9, we make sure that these guys' levels are already populated, right? Because this is good. This is very good. So yeah, so the problem is, when we're parsing this node, right, it's the very first one at its level. So, it'll be like, oh, there are no others at my level yet. I have no cousins, right? And then we never go back to this node again. But then when we get to 7, we're like, oh, yeah, dude, 7 is cousins with 1 and 10, actually, right? But then 1 never got the chance to see that it was cousins with 7. So what we do is we say, hey, when we are at 4 and 9, we're going to be like, okay, this dude, I haven't even visited him yet, but I'm going to make sure that everyone knows that this dude is at level 3 and that this dude is at level 3, right? And this dude is going to say, oh, yo, I'm going to make sure that everyone knows this dude is at level 3, right? And then what this does is like, oh my gosh, when we get to this guy, he's at level 3, and he's like, bro, there's a lot of people at level 3, including 10 and 7. And it's like, oh my god, 7 is not even with the same papa either. This is crazy wild. And adds its sum there, right? So that's how that works. And what's nice, one thing I'm realizing is like, yeah, the two children of a direct parent are going to have the same value, right? So okay. Now I just have to be able to map the values correctly, right? This is O of n squared. I don't like this. Well, it just means for each level, I'm gonna do an extra number of nodes at that level computation, right? Which is gonna be, in total, it's gonna be 1 plus 2 plus 4. Actually, it might work out, right? Where it's like, if the tree is balanced, then it'll be 1 plus 2 plus 4, but it'll be n squared upon log n. So it'll be log square of n. And then if the tree is unbalanced, then yeah, the height is n. But then there's only one node per level. So it'll be 1 plus 1 plus 1 plus 1, or 0 plus 0 plus 0, but it'll be O of n. So it'll literally either be between O of n and log squared of n. It's actually not n squared. Oh, that's actually kind of beautiful. I was thinking of it in terms of worst case of, both sides, right? It's like unbalanced tree and balanced tree superposition. But yeah, in one extreme case it's log squared of n, and another is actually O of n. So this is actually, okay, so this probably is the expected solution. Okay. Now we're just going to make sure that we populate the nodes in order, right? Oh. This is actually very easy. Right, for each node, we know its depth. Get replacement value self, comma node. Depth is equal to self dot node to depth of node. Parent is equal to node dot ooh. Self dot node to parent. Okay, well noted. So here we'll say node to parent. Okay, we can ignore this guy, right? I'm not using it anymore. But if root dot left, then yeah. Then we'll also say that self dot node to parent of root dot left and for the very first node, it's fine because that value is always 0, right? Or we can give it a parent of none. Right? We might as well just do that. Okay, we could just do a check, if parent is equal to none. And return 0. The root's always going to be 0. Then, okay. Okay, I should stop snacking on the nuts. That's not the healthiest thing in the world. Okay. Depth is equal to that, parent is equal to that. Then yeah, okay. But we really just don't need this, ideally. Well, okay, first of all, self.depths. That must be the case, sorry. If parent not in self.depths of depth, turn 0. Actually, that's not the way it's going to work, right? Wait, okay. Let's think about this. This is my papa's value. Oh no. That is going to be their value, right? Because of the way it was computed. This is for whenever there's not papa and parent. Okay, this is good. We can do return self.depths of depth dot get parent comma 0. Def in order depth replace tree. Jeez. Yeah, I should not have used my peanuts. Now I'm getting my keyboard sticky. Okay. Replace tree. Self, comma. Or we could call it update tree, or yeah. Update tree. With roots. And here we'll say, hey. Not roots. Return roots. Root.val is equal to self.get replacement value of root. Left is equal to dot left. Same thing for this guy, but with right, and return root. And now here we'll do return self.update tree with roots. Oh. Which one is it? It's root, isn't it? Or is it not? It is. Val 5. Yeah. Self dot, what is it called? Node to depth of root is equal to 0. Val 4. Interesting. Oh, do I not update it in here? Wait, that's wild. Okay, maybe we don't need this here. Oh, yeah. We do. Just that here should be self.node to depth of root.left is equal to depth plus 1. Right? And then here it should be of root.right is equal to depth plus 1. Whoa, 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 whoa. What is going on? What? What's the error? Int object has no attribute left. Oh. But where am I using this? Yeah, here I'm doing root.right. 76. What is going on? Please, please. Okay. This is wild. If root.left, then start doing stuff with root.left. If root.right, then start doing stuff with root.right. This is crazy. Actually, we know this, right? Node to parent of root is equal to parent. Self.node to depth of root is equal to depth. Now we can comment this out. Comment this out. Brother. Okay, it is an int. But where else am I using this is like with a dot left? I'm not doing like depth dot left or anything. Print self dot depths. Jeez. This is wild. What is this error? Object has no attribute left. When am I calling dot left? Was it because of this? Okay, that's why, isn't it? If I do return root, everything is gangster. Ah, okay. Okay. So yeah, it's because I'm modifying the tree when I'm using the same hash objects. Okay. Really what I should do is just what? Like modify. Yeah, just modifying the values is not good. So maybe I just create a clone of the tree. So yeah, if not root, return none. Here we'll say new root node is equal to or copy root or new root is equal to a tree node with root.value. Right? New root.left Oh, I'm dumb. Wait. First of all, why am I not doing update tree here? Okay, well, oh my goodness, that's why. Well, obviously I'm setting those to the values. Okay, well that's not frustrating at all. Okay, so let's hit submit, see if this works. We might get like an output limit exceeded. Yeah, so that's no worries. We can essentially go to wherever we have a print. Here we can do that. Can cancel that guy. So let's just add this guy in here. Let's run these guys. Okay. Let's wait let's wait a few seconds. Okay, so now let's resubmit. Is it too slow? Too slow, isn't it? Time limit exceeded. I see. Okay. Good to know. This is too slow. I really thought it wouldn't be n squared. Either log squared n or O of n. Interesting. Yeah, this is a huge input. Okay. So yeah, that's fine. I can remove this assert if anything. I still time limit exceed. Interesting. So how do you do this, right? How are you going to get all the cousins sum when most nodes at your level will be your cousin? Unless you do something where it's like, hey, each node is the sum of your level, right? If I do each node is the sum of its level, and then I essentially say like, okay, Okay, wait. That would work. If I do each node as the sum of its level, and then I subtract all the things inside of its parent, then it's GG. Okay. Right? Like, if I do something like, here I have my 5. Oh, goodness. Okay, let's just do triple quotes. I have something like my 5 here, my 4, and my 9. And this is my 1. This is my 10. So you know what? Let's move this guy even more. Move this guy even more. My 7. Right. And there we go. It was just a little awkward, but yeah. Okay. Then it's like this will essentially transform into this. So some of this level is 5, some of this level is what? 4 plus 9 is 13. Become a 13. And this will become 1 plus, so 17, 18. Become an 18. Become 18. This will become 18. And then this becomes, so really it should be, I copy this, and it's like, okay, the sum of this, of where with this parent is equal to 11, right? Actually, okay, the root node is 0. Root node becomes 0. Then the parent of the root, so the ones that have the parent as the root node will have the sum of that discarded, right? So this guy's parent is 5. The sum of the two children below 5 is equal to 13. So this gets minus 13, which becomes 0. This becomes 0. Oh, and it's at most 2 nodes at a time. Then it's like, okay, the guy here had a parent of 4. It had an O value of 1 and 10, right? So I subtract 11. So here if I subtract 11, that 18 minus 11 is 7. And here this becomes 7. Then here it's like, okay, over here there was nothing to the left, so that's effectively 0. Plus 7, I will subtract 7. 18 minus 7 is equal to 11. Yeah, okay, so that's essentially the idea. Makes sense. Okay, so yeah, I figured that it would be something like that, right? Because it's like, how do you solve this problem without going n squared mode, right? That's essentially how. Okay, that's cool, that's cool. I'm glad we figured this out. So now it's just coding it up then, right? Okay. So we gotta modify our code. Now the thing is, do we want to do a full modification of the tree this way, right? Essentially, it's like to get the value. Yeah, you want the level sums, right? So, okay, we definitely should populate level sums. One easy way to populate level sums. Okay, here we'll do self.level sums. Level sums. Let's go to this. Okay, first of all, populate depths. You can just, there you go. We'll even get rid of it. Level sums. Actually, we'll call level sums. We'll call it depth sums. of depth equals self.depth sums dot get depth or default value of 0 plus root.val. Okay, so for each node it's going to be the sum of its depth minus, you're going to go to daddy and you're going to subtract from it both of daddy's children's. I know this sounds old, sounds funny, but yeah. Def get replacement value with self comma node will be level sum sum of depth minus the only problem is if I'm modifying the tree, this can cause problems, right? Because it's like if I modify myself and then I use that node in another node's calculations, well then, whoopsie, right? Maybe I do self dot node to new value replacement value was this. Go to replacement value. Self.new node to new value. Okay, so minus sum of parents, children, original values. So here we'll do this same thing. Res is equal to self dot depth sums of depth. If parent dot left, res minus or equal to parent dot left dot val. If parent dot right, res minus or equal to parent dot right dot val. And then here we'll say I return res. Here we'll say def update tree. Yeah. Def generate replacement values self comma root. Here we'll say yeah. We'll just do two parses of the tree. If not root, return none. Yeah, get replacement value. Value of root self.get replacement value of root. Right, and now update tree. So from root and then update tree. To new value of root, something like this, except for none types. If not parent, must be root node. So return 0. Return 0. My gosh. Oh, yeah. That would make sense. We're still gonna TLE? That is wild. Interesting. Okay, let's get rid of the test case. I want to still see if we are passing at least. Okay, so that worked. It's definitely a much better idea, right? So, okay, so now we can just churn down on the time complexity of these things. So to get a replacement value, what do we need? We need the depth and we need daddy. So yeah, essentially, all we need is we need depth and daddy. Okay. All we need for each node is its depth and daddy and parent. We also need to know level sums. Okay. So now what I'm gonna do is I'm gonna restart this entire problem. And there we go. And now we're just gonna call on from here. Right? So here's now we're gonna do definite self.node to depth and daddy pair. Def get depth. Self, node. Actually here, yeah. Node to depth. You might as well do self.node to daddy. Instead of having pairs, you might as well have two dictionaries. It's the same amount of memory anyways, right? Here we'll have return assert node in self.node to depth, and then return self.node to depth of node. Def get parent, node to parent, self comma node, node and self.node to parent, return self.node to parent of node. Okay, now we can just get along with this, right? So def populate depths and parent pairs. Depths and parents, self comma root. So here we'll do self dot this first with the root. If not root, return, and we should have a depth and a daddy, which at the beginning is none. Otherwise, here we've got a depth and we've got daddy. So parents. Okay, I should stop saying daddy. It's parent. It's parent. Okay. Now that we have that, it's like, okay, if not root, return. Otherwise, we're going to say self.node to depth of root is equal to depth. Self.node to parent of root is equal to parent. And we're going to just do self.populate this with root.left, self.populate this with root.right, and return. And here we're going to do print there we go. Yeah, so this should be populated correctly, right? Print self.node to depth. Print self.node to parent turn on. Yeah, here we're going to do depth plus 1 and root is your daddy. Depth plus 1 and root is your daddy. Okay. Yeah, so as expected, this is just huge. Print delimiter. So yeah, this is just too big to see anything. Yeah, something maps to 1, something maps to 2. For node in self.node to depth, print f string node.val equals depth equals. For node in self.node to parent, print f string node.val equals parent.val equals. Node.val equals parent.val if parent else -1. Float of negative infinity. Because of the root node, right? And else, you know what, we'll just do -1. Self.node to depth of node. Depth equals self.node to depth of node. Parent is equal to self.node to parent of node. There we go. Okay, so now let's look at this, right? Yeah, 5 has a depth of 0, 4 has a depth of 1, 1 has a depth of 2, 10 has a depth of 2, 9 depth of 1, 7 depth of 2. This is very good. In fact, why don't we just do this in order? In order traversal. Actually, it doesn't even matter. A dictionary's ordering is random. What am I thinking? Okay. What I want is probably like pre-order. But even that pre-order goes in that way. That's fine. 5, 4, 1, 10, 9, 7. Yeah, so that's good. And then, yeah, 5 has no parent. 4 has a parent of 5. 1 is a parent of 4. 10 has a parent of 4. 9 has a parent of 5. And 7 is the parent of 9. Okay, so these are populated pretty correctly. Okay, so that's great. That's actually fantastic. Now, we also need to know the level sums, right? Self.level sums, or self.depth sums. What is this? Depth sums of depth sums dot get depth comma 0 plus root of that. Print delimiter for node in self dot level sum. Print self dot depth sums. Okay, 0 to yeah, so this is a yeah, 13, 18. Okay, this is perfect. Then from here on, we're just gonna come up with the same idea. So one way we can do it is just generate everything as we need. Okay, so we have all the data that we need, right? Now, what we need is def generate replacement values, self, root, right? If not root, return. And then here it's like self dot replacement node to replacement value. Let's go to this. There we go. Replacement values. Maps nodes to their replacement values. The other ones are obvious. And yeah. Otherwise, res is equal to self dot level. Yeah. So first of all, depth is equal to self dot node to depth of root. Parent is equal to self dot node to parent of root. Self dot level sums of depth. Parent dot left. Res minus or equal to parent dot left dot val. If parent dot right, res minus or equal to parent dot right dot val. And that's constant work right there, so that's good. And then here it's like self dot replacement values node to replacement value. There we go. Of root is equal to res. Return. And then here we'll do the same things. Self dot this root dot left, and same thing. Self dot generate root dot right. Return. And there we go. Okay. So now we have the replacement values. So let's print that real quick. For node in self dot node to replacement value. Replacement value is equal to of node print f string node.val is equal replacement value is equal. So now let's print that. Okay. Oh yeah, now we need to do self dot of root. Okay, anywhere that has level sums needs to be replaced with depth sums. There we go. If not parent, root node is special case, and value is always 0. Return 0. Yeah. Yeah, you don't want to just return 0 preemptively. You know what? Right, self dot You know, let's replace all this. We'll call this the helper. Self, root. We'll have this. Node. Of of root is equal to 0. Values helper. Helper. There we go. If root dot left, and there we go. If root dot right, and here we go. Are you kidding me? Why is the root none? What test case do I have that the root is actually none? Oh my goodness. Oh, because I don't, oh my goodness. I should have these. True or. So these I do need. But the problem is that this should essentially be, yeah, you should call the helper. There you go. But there will be a case where I fail because I have this. So yeah, this is good to do. Right? And the number of nodes is at least 1, right? So there's at least a root. So that's good. Okay. So instead of having the code inside of here directly, we'll just have that which calls in the actual helper, which is actually the logic code we want, just because of code cleanliness. Okay, and then now we have everything we want. So now we just call a function called update tree. Update tree. Not roots. Return none. Root.val is equal to these are useless. Right? It is equal to this, right? Root. The update tree. To the left, root dot right, self tree dot right, return. Now here, what I'll do is turn self.update tree with roots. That's wrong somehow. Return root. Oh my goodness. Okay, so now that's accepted. And now let's comment this out. And now I pray that this works. If this doesn't work, then it'll be hard to come up with a new idea. So hopefully this is fast enough this time. Okay, and it is fast enough. Perfect. Bada bing, bada boom. And it's super fast, actually, 91%. There we go. Okay, very nice. Oh, that's wonderful. Okay, so we can just clean up a lot of this code. Honestly, I think it was a good idea to just, once I figured out the idea that I needed to do, that we just essentially, I restart the problem, start from a clean slate, add this little comment. Basically, it's like I did an hour worth of work to figure out what is the efficient idea, and I didn't want to just go through my own code and start editing stuff until it works. I was like, it'll be even faster to just start from a clean slate and just keep going from there, right? I have the idea in my mind, and there we go. So okay, I need all these things, I need these things, There we go. There we go. Whoops. Populate depths and parents. That's fine. This is fine. There we go. Yeah, this is fine. Yeah, this is fine. Okay, so it's all nice, beautiful, and fine. Okay, so let's drink some water. And there we go. Okay, so it seems like a, 418 ms, but this is a very nice and efficient solution. So bada bing, bada boom. That's pretty much it. And okay, so as always, in all my videos, I do a quick recap of how I was able to solve the problem. So essentially for this one, it was very, very tricky, because one thing you have to realize is like, okay, for each root in the binary tree, replace the value of each node in the tree with the sum of all of its cousins' values, where cousin is defined if it has the same depth but with a different parent, right? And so one thing that you quickly realize is that so first of all, cousins are limited to, given a node, the possible candidates for the cousins are limited to the nodes at the same level, right? So for example, this 10 is at level 3 here, right? If this is level 1, level 2, level or depth of 1, depth of 2, depth of 3, really based on their definition here. This is technically depth of 0, depth of 1, depth of 2. You know what, just to make it easy for this, to be consistent with this, we'll just call it that, right? So this is depth of 0, depth of 1, depth of 2. So this 10, for example, is at a depth of level 2, right? So depth 2, you cannot have a cousin at depth 1, right? 9 and 10 will not be cousins of each other. But 10 can be a cousin of anything else that's also at a depth of 2, right? 1 is at a depth of 2, and 7 is at a depth of 2, right? And it's only a cousin of 7 because 7 is at a depth of it has a different parent of value 9 here than this one of value 4 over here, right? So since 10 and 7 are both at the same level and they are or have different parents, then they're essentially cousins of each other, right? And so essentially the trivial way is like, you know, you get each level, you get the parent for each level, and then for each node, it's like go through all the other parents that are not your own, add your current value to that sum, and so on. But one thing you quickly realize with that approach is that you end up with a closer to n squared solution, or at least a not optimal solution. I thought it was like log squared n plus O of n because of some calculation I made, but for now let's just pretend that it's something like O of n squared. The point is that a time limit exceeds it, so it was too slow of a solution. And so one thing that I realized is like, okay, we need a way to essentially do the same thing much more efficiently, right? Where it's like I really need to skip the part of like, you know, going through every single parent that is not my own and adding the value to there, because that is a lot of work, right? For each node, I might be going to each other node inside of my level, which, like, you know, might be like 1 plus 2 plus 4 plus 8. It's like it starts getting exponentially large, right? Or like depending on the height of the tree, like that's why, because even if it's, you know, the length, the height of the tree is equal to the number of nodes, then it's only like, you know, one thing per level, so therefore it's very cheap. Otherwise, you know, if it's perfectly balanced, then it's like, yeah, it'll be like 1 plus 2 plus 4, which is huge, but it'll be limited to log n, right? So it'll be like, you know, 1 plus 2 plus all the way up to log n, so it'll be the squaring of that, so O of log squared of n. So I thought it would be like, you know, between O of n and log squared of n, but I guess it's too slow anyways, right? Because it's like you're doing n times that, right? And so if they give you a bad tree, I guess maybe it is n squared. So maybe the overall time complexity is like, you know, O of n squared plus O of n log squared n, and that's just too slow, right? So that makes sense. Then, for something like this, one thing I realized is like, okay, at a level, most nodes will actually be my cousin, right? It's like if you have, I used to have good examples over here that I drew before. I'll just undo these functions over here. It's like if I have something like, you know, okay, maybe I don't draw it, but like you could imagine, like, you know, as the tree gets huge, right? It's like, let's say we have a bunch of these guys like next to each other, like this, and it's like here this shares parent of A, these two share a parent of B, these two share a parent of C, and these two share a parent of D, right? And like let's say that, like, you know, these share a parent of like X, these share a parent of like Y, and like these two share a parent like Z, right? So it's like, imagine a binary tree right like that, right? So like Z's children are X and Y, here A and B, C and D, and then these guys here, right? So something like 3 will actually be cousins with 1, 2, 5, 6, 7, and 8. It will just not be a cousin with itself because it has its own parent, right? And 4. So the thing to realize is that most nodes at a certain level, right? So or depth, right? This is all the same depth or level here, right? So if this is depth 0, depth 1, depth 2, depth 3. So at depth 3, this is depth 3, right? What you'll notice is if you pick out a random node like 3, most nodes at that depth will actually be cousins with 3. It won't be the other way, right? It won't be that most nodes are not cousins with 3. 3 is actually cousins with most nodes at this depth, right? So that's what makes this a little tricky, right? Where it's like, okay, you have to recognize that fact that it's cousins with most nodes. And so what nodes is it not cousins with, right? Well, it's not cousins with anything that comes from its own parent. And now here's the cool thing. This is a binary tree, right? So any parent, right, any node can have at most 2 children, 2 children. So what I can do is like, okay, I'm going to say I am cousins with everybody except whatever children comes out of my parent, right? So for 3's parents, it's going to be B, right? Once I grab 3's parent of B, I say like, okay, it's essentially going to be the sum of everything in here minus the sum of the children of B, right? Which includes my own node of 3 here and the other node that comes out of the same parent of 4. But this makes sense, right? Because it's like, what are the cousins of 3 that are at the same depth and, you know, have a different parent? Well, it's going to be, well, 1, because 1's parent is A and it's not B, right? So 1 plus 2, 3 and 4, like from B, that's not allowed. So the next one is like, you know, 5 because it has a different parent of C. So 5 plus 6 plus 7 plus 8. But essentially, what that means is like, for each node, its replacement value will essentially be the sum of the whole level minus the value of its own parents' children, which includes itself, of course. Because again, it's like you have to recognize the fact that like if something is going to be a cousin with most of the nodes at its level, it's only not going to be cousins with the things that share its own parent. Well, the parent can only contain at most one other node, right? The point is it's a binary tree, so every node can have at most 2 children. So it's constant time work to subtract the value of, you know, the sum of the children of your direct parent, right? So that's essentially the idea that I utilize, because it's like I can compute the sum of this entire level once, and then for each node, like for example, like a node like 5, it'll be like, okay, I'll grab whatever sum this is, right? 1 plus 2 plus all the way up to 8, this should be like, you know, that should be 36. Is it 36? 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, 14, 19, 25, 7 plus 8 is what, 15? So this is 40. What was I missing? Is it times n plus 1? Wait, no. I thought it was 8 times 9 divided by 2. Am I stupid? I thought it was like, you know, if you had something like 1 plus dot 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 plus n, this is equal to n times n plus 1 over 2. So here it's like 8 times 9 over 2 is equal to 4 times 9, which is 36, right? So this is 3, that makes it 6, that makes it 10, 15, 21, and then plus 15. Then yeah, that does equal 36. Okay, I'm being done. Sorry, little side tangent there, right? But the point is that the sum here is equal to, sum is equal to 36, right? And so for something like 3 here, essentially going to be that sum of 36, which I can just compute once, and I subtract from it, you know, I get its parent, and I say, okay, for whatever children are the children of this parent, I'm going to subtract their values, right? So in this case, it's 3, the node itself, and 4, because that one also exists, right? If there's a node that, like, you know, doesn't exist, and I'm trying to get it for 7, then I'm going to go to this parent, and I'm going to see there's no right child, then I don't do anything, right? It's almost as if though there was a value of 0, right? It's a ghost. There is no the cousin to consider here, so it didn't affect the sum in the first place, so it's like, it's fine, right? But the point is that, like, okay, for each node, essentially, its replacement value will be the sum of its level, or the sum of it, the sum of the values of all the nodes at its depth. So in this case, like at the depth of 3, it'll be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, which is equal to 36. And from that point onwards, essentially, we'll say that, yeah, okay. Again, it's just that it'll be the sum of all of the values of the nodes at that depth minus, for each node, the sum of the values of the node that belong to the children of that node's parent, right? Again, it's a huge play on words, but essentially for, like, you know, if we look at a node like 1, essentially it'll be like whatever sum this is, so that's 36, right? Minus the two children that belong to this parent. So for 1, its parent is A. So for A, we're gonna say, okay, whatever children it has, we're gonna subtract their values. So the left child has 1, so we're gonna subtract 1, and the right child has 2, so we're gonna subtract 2. And why do we do this? Because it's like, okay, a cousin of 1 must be at the same depth, right? Which is why we take the sum of all the numbers at that depth, right? Because we can only consider the things at the same depth. So we're not going to start adding whatever numbers are in here. We're only going to add the ones that are at the same depth. And it must be the fact that they have different parents. Well, only at most one other node can have the same parent, right? So from 1, it has a parent of A. At most one other node can have that same parent. In this case, it's 2. Every other node at this depth will have a different parent. So it's actually cheaper to get the sum of the values of the nodes at that depth and then subtract the ones that have the same parent than it is to do the other way around. And that's why essentially when I redid this problem and I did it in this way, obviously we don't time limit exceed it anymore. With the other way being like, you know, don't pre-compute the sum and like for each one, like, you know, loop through all the parents that are not your own, grab all these and so on, add them together and so on. So you end up doing like, you know, n squared work, right? So like for this one, I end up, you know, adding all these values. For this one, I end up adding all of these values. For this one, I end up adding these two values plus these values and so on. And that's like very, very, very expensive as opposed to doing it this way because again, how many children does a parent have? At most 2. So it's O of 1 work in order to compute the sum of the 2 direct children of a node's sum and value. So hopefully that explanation made sense. And again, the rest of it is just coding it up, right? So essentially what I do is the very first thing is I populate the depth and parents for each node. So for each node, essentially, I have a hash map here that says like, you know, node to depth and node to parent. So essentially for every single node in the tree, I will have a mapping from that node to its depth level as well as that node to its parent level, right? And also for each depth, I will essentially compute the sum of all the values of the nodes at that depth level, right? And I just do this just recursively, very simply, where it's like, okay, like I pass in, you know, originally the original root, I give it a depth of 0 initially, and it has no parent, so I give it none here. And so it's like, okay, if not root, return. Otherwise, it's like, okay, I have my root, depth, and parent, right? So node to depth of root, very simple. It's whatever depth I pass in here, right? Node to parent of root, very simple. It's whatever parent I pass in here, right? And then the depth sums of depth, if it doesn't exist yet, I initialize it with a value of 0. Otherwise, I get its current value, and to it, I add this current node's value, right? Because it belongs at this depth. So whatever value of depth sums I have at this depth, I'm going to add root.val, and initially it's going to be 0 plus root.val if it's the very first time that I add to this depth level, right? Otherwise, I'm just going to recursively call this for the left and right subtrees. So for root.left, let's think about its new depth. Well, it's going to be what current depth I'm on plus 1, right? Because I'm going one level deeper. So depth plus 1 makes sense here. And then for both root.left and root.right, what are going to be its parent? Well, the root itself. So that's why I pass root in as the parent here. And there you go. I just populate all these values recursively in here for node to depth, node to parent, and depth sums. And once I have that, it's very simple, right? Essentially what I do is I call this generate replacement values function, which just says like, hey, okay, this is just a little helper because the root node is a special case, but really what matters is this stuff where it's like, okay, if not root, then return. Otherwise, it's like, okay, for every node in the tree, I'm essentially going to grab its depth because now I've computed a mapping of all the nodes to their depth, so I can get this in O of 1 time. I can get the parent now in O of 1 time as well, thanks to my pre-computation, and I can get, you know, the current sum of the depths that we were talking about. So like it would be like, you know, the depth sum here, which is equal to 36 in this example. And then I say, okay, I know the parent. Let's look at the parent. If the parent has a left child, I'm going to subtract from the sum of this depth that parent's left child's value, right? Because again, this is not a valid cousin, including its own self, right? And then if parent right, you know, if the parent has a right child, even if it's yourself or, you know, the only other possible node that could have been not your cousin at the same depth. And again, I subtract that from my result, just like I explained earlier. So it's like in the case of 3, or in the case of 1, it's the same as like, you know, grabbing the whole sum and then subtracting the value of this guy and this guy because they both share the same parent of A, which is 1's parent. And then from then on, then it's like, okay, node to replacement value. I'm just going to map every single node to its new replacement value, which we just calculated up here. So I set that equal to res, and then I do that for, you know, root.left and root.right recursively, so that I map every single node to its new replacement value. And now once I have each node and the replacement value that they should have, I do one last call here. I call one more method called self.updateTree, which I return. And essentially what this does is like, okay, if not root, then just return none, i.e. if root is none, return none. Otherwise, it's like, okay, this current root's value is going to be replaced with, well, whatever we calculated for its replacement value up top, right? Node to replacement value of that root. And then again, recursively do this for the left and right subtrees, and then return the new tree with, you know, every single value inside the tree replaced with its calculated replacement value that we generated over here inside this generate replacement values helper function, right? And then once I have that, I just return that tree with all the updated values. I just return, and therefore it works. We can run this one more time. You'll see that this works just nice and perfectly. We can even submit it one more time, and I think it's pretty efficient as long as we don't get unlucky. So let's just see. And then, yeah, so it just beats 91.96% for 12 ms. So just very nice, very cool solution, and also happens to be very fast. So bada bing, bada boom, that's pretty much it. And hopefully the explanation makes sense in terms of how I was able to solve the problem. And it's also very, very exciting because now I'm at 99 problems solved, which means that tomorrow will actually be day 100 of me doing this daily LeetCode challenge journey, which will be a very cool feat and milestone. So that's pretty much it. Yeah, just submitting here one more time because I had that little comment block that I want to get rid of. And oh, nice, we saved a little bit of ms, so now we're 92%. But yeah, it seems like we're in this range and so on. So we have a reasonably optimal solution. I'm guessing people are here at the 90 ms because usually when that happens is because this question used to have much less test cases and so on. Or actually, maybe, you know, people found out a way to do essentially the same thing as me, but like, you know, I might parse the tree like, you know, more than one time, which is still like, you know, O of n, like if you parse the tree like, you know, 4 times, it's just 4n is still O of n and so on. But again, like if they reduced it by like 4, then yeah, it makes sense, right? So 400 roughly divided by 4 is about 100 ms. So like, you know, maybe some people figured out how to do this in one parse, which is yeah, you know, good for them and so on. But time complexity wise, this is the very, very same time complexity. So that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.